Hello everyone, welcome back to MAC1105. In this video, we're going to jump to another type of function, and this type of function is the one we already I already mentioned in the previous section when the first time I introduced all basic function of college algebra. This function is rational function. However, in this video, we're gonna discuss more about the domain of rational function as well as the ending behavior when x approaches to positive and negative infinities. What is happening to the graph of this of rational function? Okay, so let's get started. So let me put the topic today: rational function. Alright, again, in the first part of the lecture, let's talk about the definition of rational function. What does rational function look like? As we already know, rational expression is an algebraic expression that contains numerator and denominator, because especially it must have a variable under the denominator. So for rational function, it's a function. It's in fractional form. It's also has numerator and denominator, and at the denominator it contains the x variable. Okay. Besides, in the numerator and denominator, they are polynomial function. They are polynomial expression. Okay. So the rational function could be look like this: f of x. I think I'm going to use a different color here. F of x equal to on the top we will have a polynomial expression, so we have p of x, so that's this polynomial expression, and the bottom we have q of x, which is another polynomial. Okay, so p of x and q of x, they are polynomial. Okay, they are polynomial function. Okay, and of course q of x must be different from 0, because if it's 0 then it's undefined, right? Okay. Because p of x and q of x are polynomial, so, and we know that there's some condition for the algebraic expression to be called polynomial. The degree, the exponent must be positive, right? Okay, the exponent must be positive. And the exponent, it cannot be fraction or irrational number. Like, for example, like if the exponent is square root of 2, then it's not considered as a polynomial anymore. Or the variable x, if the variable x is like something else, so like 1 over x, right? Then it's not called polynomial anymore. Okay. For example, I have something like this. Example number 1. I have f of x equal to how about like this? I have make it a simple one. Okay, let's do the simple one first. The one we already talked about in the previous section, 1 over x. So this is a very simple one. Okay, this is rational function. Okay, and the graph of this function I already introduced in the video, in the lecture when I first time introduced function. So the graph of the sketch of this function will be something like this. Will be something like that. One branch over here and the other branch over here. X here and y here, and these two branches here. Okay, let me redraw it. These two branches here, it never crossed the x and y axis. It never crossed x and y axis. So it means that x and y axis over here is asymptote. So they are asymptote right here. So this is asymptote. It's called horizontal asymptote. Okay, because you see the graph is never crossed, and this one we call the vertical asymptote. Okay, anyone remember the domain and range of this one? Actually, I already also mentioned this before. You see that it never crosses zeros, right? So the domain will go from negative infinity. Let's just go from negative infinity, go to 0. Domain, look at x, okay? Union with 0 to positive infinity. That's the domain. And so is the range. Negative infinity to 0. Union with 0 to positive. Okay. So this is very basic. This is like we call it the parent function of rational function. So from this function we can transform, right? We can apply transformation concept to derive a more complicated function. Or another rational function I already mentioned in the previous section, which is this one, f of x equal to 1 over x squared. And the graph for this one will be something like this. This is the x-axis here, and this is the y-axis here. And the graph of this one will be something like that. Going up like that. And we have another branch going down like this. So in this case, the x and y, axis and y is also a vertical and a horizontal asymptote. And the domain over here will be the same. The domain will be negative infinity to 0, union with 0 to positive infinity. However, the range will be different because you see the range, we don't have the bottom part right here. So the range, look at the one, will start from 0, which is not included, to positive infinity. Okay? Okay? To positive infinity. Alright, so these are two typical examples, simple operational function. Of course, we have something more complicated. For example, like this one. For example, I have something like this, right? 2 over x plus 1. This is also rational function. Okay. Actually, it's look like this, right? But you plus 1 and plus 1 is so basically if you apply this transformation concept, basically you move it to the left one unit right here. Of course, then we have 2, so it's a little bit different also. But the shape is kind of like that. Okay. Or we have something like this. Or we have something like this. Something more complicated. How about like this? I have equal to x plus 1 over 2x squared, alright, plus 5x minus 3. You know, this is also rational function. It's also right because the top and the bottom is polynomial. The top and the bottom is polynomial. So how are we going to find the domain? In order to find the domain, because the denominator cannot be 0, so you have to set x plus 1 different from 0. So from here we solve for x. So x must be different from negative 1. And if x different from the negative 1, so the domain will be negative infinity to negative 1, not included because it's different from. Okay? Not included, negative 1 to positive infinity. So in order to find the domain here, all you have to do is you gotta go ahead and factor them out. If it is factorable, go ahead. So let's see if it can be factored. So we have 2x x over here. So I have plus 3 minus 1. Yep. Alright, so now we're gonna set 2x minus 1 different from 0. And x plus 3 different from 0. We're gonna solve with 2 value here. Alright, we solve with 2 value, and you see that if you put on the number line, we're gonna exclude this 2 value. So the domain will be what? Negative infinity to negative 3, union negative 3 to a half, and union a half to positive infinity. Okay. That's how you find the domain for rational function. Of course, there's more different type of rational function. Example, if I can have something like this. I can have x squared plus 1 on the top, and the bottom I have x minus 2. Okay, it could be something like that. You see that the degree over here is smaller than this, the degree over here is smaller, but the degree of the top here is bigger than the degree here. Or I can have something with the degree it is same. For example, like this, 2x minus 1, and over here x minus 3. So this is the first degree, and this is also the first degree. So it could be the degree could be the same, or it could be smaller, or it could be greater on the top. Okay, could be anything. All right. Okay. And in order to find the domain here, you're gonna do the same as example number 3. Okay. Now in example number 7, for example, I have something like this. I have g of x equal to 3x squared minus 3x minus 6 over x squared plus ax plus 16. Alright, so I have a rational. You see the degree is the same, the top and the bottom degree is the same. Now in the first part, I want you to find domain. On the second part, I want you to find x and y intercept point. X and y intercept point. Okay. Let's see. What else can I ask here? Yep, I think I'm gonna just ask 2 questions at this moment. Then later on we're gonna do more example. We're gonna ask you more. So let's find the domain first. Alright, in order to find the domain, you gotta factor this one out. Let's see if it is factorable. Again, you gotta set the denominator different from 0. Now let's go ahead and factor them out. X plus 4, right? So over here, x different from negative 4. So negative 4 cannot be included in the domain. So the domain will be negative infinity to negative 4 union negative 4 to positive infinity. That's the domain. In order to find x and y intercept, point, you're gonna replace y with 0. So I'm gonna replace this with 0. Okay. We are finding x intercept point. Okay. So I multiply both sides by the denominator. So what I have will be 3x squared plus 3x minus 6. And again, I'm gonna go ahead and try to factor them. Hopefully it's factorable. So I have 3x here and x over here. So I'm gonna have 3 over here and 2 over here. So the answer will be minus plus 3. Here you go. So if I apply the zero product property, okay, so over here I'm gonna have x equal to negative 1 and x equal to 2. So the x-intercept point, okay, so x-intercept point will be in order pair form, okay, so it will be negative 1, 0 and 2, 0. So we have 2 x-intercept point. How about y-intercept point? In order to find y-intercept point, you're gonna replace x with 0. So you have 3, 0 square minus 3, 0 minus 6 over square 16. So you have negative 6 over 16, which is negative 3 over 8. So y-intercept point will be what? Will be 0 minus 3 over 8. Here you go. That's y-intercept point. Actually, the concept of x-intercept and y-intercept we've been doing so many times already, right? When first time you introduce to x and y-intercept upon concepts in the intermediate algebra course. Okay, so this is you're going to do the same. Okay, so it's not really that hard. Okay, and again, in order to find the domain of rational function, you just have to set the denominator different from 0. Of course, some rational function is harder to find a domain, but you have to factor them out. If it is factorable, then if the denominator is factorable, that would be very easy. Okay, but if it's not factorable, then of course in order to find the domain of that rational function will be tough. Okay, it will be easy. So most of the time, the problem I give you, or you see in the MATLAB, will have it has a denominator factorable. Okay, if it is factorable, then you know the value you put on the number line, and you will see the domain, because that value will be excluded from the domain. So I'm sure you don't have to use a bracket for that. It must be parentheses. Okay. Okay. Now, if you notice, you see that on the first two examples, the rational function always has vertical asymptote and horizontal asymptote. But the question is whether or not they have vertical asymptote and horizontal asymptote all the time. Or maybe they have just one of them, or maybe they have a different type of asymptote. So in the second part of the video, I just want to make sure that I'm not missing anything else. See, before we talking about the asymptote, so we already we talk about domain and range. Okay. I don't know if I should give you a problem that's more complicated than that, or maybe that one is good enough. Yeah, I think that one is good enough. You know, it's kind of standard. But let me check really quick over here. Yeah. Okay, so all of them look like everything is very standard. Okay, so you see that all of them you have to factor them out. Okay, you have to factor them out. All right. How about this one? This is a very interesting problem right here. X squared minus 4 and x minus 2. So let's do one more problem. One more example. Example number 8. Okay. Example number 8. I have g of x here. X squared minus 4, x minus 2. Okay, and if you look at the bottom, you see that you cannot factor anymore. However, if, on the top is a different of square, you can go ahead and factor them. Okay, factor them. And when you factor, what's happening here? You can cancel them out, right? So you have x plus 2. So you have x plus 2. So what is happening here? It means that at x equal 2, okay, we have a disconnection. We call that a hole. Okay, so over here, because we cancel this, so we have disconnection in the graph. We have disconnection in the graphs. We have disconnection in the graph. Okay, that's what we noticed. And where is the disconnection? Where's that located? We can find that disconnection. Sometimes we call, in this case, we call that a hole. Okay, a hole. Alright, and we can find the coordinate for that hole. So how are we going to find this? Because we cancel x minus 2, right? So if we go ahead and set it equal to 0, so you have x equal 2. Okay. Then we're going to plug it into the function after we cancel. So plug it over here, so we have y equal 2 plus 2, plug 2 over here, plug this 2 over here, give you 4. Then the coordinate of the whole, okay, the coordinate of the whole coordinate will be what? Will be 2, 4. Ah, that's a very interesting information right there, huh? Now look at that. Let's see if we've got them right or not. Look at it. Oh, they never mentioned that, but that's good to know. It's good to know. Okay, they never mentioned about the whole, but that's okay. I mean, we learned something new. Okay, they should mention that. Okay, they should mention it. Let me see. They probably mentioned at the end. That's okay. So that is called a whole. It means that at x equal at the point 2 and 4, you know, we have a disconnection 2 and 4 right over there. We call that a whole. Okay. It's kind of surprising to me that they never mentioned that term. Oh, right here. Oh, right here. There you go. I see that. I see the term right now. A hole. There's a hole right there. You see that? So it means that there's a disconnection. This is an interesting problem. Example. I can give you another example where we have a very something really strange about the domain. How about what if I have this x squared minus 3x plus 1 on the top, and the bottom, what happened at the bottom is x squared plus 4. Okay, what happening here? If you see the x squared plus 4, and no matter what value you plug in the denominator, you always able to evaluate it. You always get the output when you plug any value for the input, right? So what does it mean here? It means that the domain in this case is always negative infinity to positive infinity. Okay, this is a very special case for that, because this is always positive. Sin. So I'm gonna put the different color here. Sin x squared plus 4 is always greater than 0. This is fact. It's true all the time. So no matter what value of x you plug over here, you always can evaluate it. I mean the domain could be negative infinity to positive infinity. Okay? Alright. On the second part of this video lecture, I want to investigate whether or not rational functions have all type of asymptote. We have 3 different type of asymptote: a vertical asymptote, a horizontal asymptote, and we also have another type we call a slanted asymptote. But whether or not they have all of them, or maybe some rational function it has only 1 or 2 type of asymptote. Alright, so the second Roman, I'm going to put here. I'm going to put over here as asymptote. Alright. Before we investigate whether or not a rational function has asymptote, we try to see like what does it mean by asymptote. Okay, and let's talk about the first type of asymptote, which is vertical asymptote. Okay, so the first type is vertical asymptote. What is vertical asymptote? Vertical asymptote is just a vertical line. That vertical line, but the graph of rational function, it never crossed that vertical line. So what does it mean? It means that when x approach to when x approaches to this is the definition of vertical asymptote. When x approaches to a value a, okay, when x approaches to the value a, then f of x approach to positive or negative infinity. So that's what I mean. So literally, this is vertical asymptote. Vertical asymptote is where the function undefined. So literally, it is where the function undefined. Okay. Okay. So it's located at where rational function undefined. Okay. Now let's go back to the one of the basic rational function right over here. The rational function over here is not defined at 0. So the vertical asymptote is right there. X equals 0. Okay, x equals 0. In some case, if the function is defined everywhere, then we don't have any vertical asymptote. Okay. Now, so how are we going to find vertical asymptote? Because this is located at where the function undefined, so the vertical asymptote can be found by just looking at the domain. Okay, look at the value where the function undefined. The value that does not belong to the domain. That's all, right? For example, find vertical asymptote. Okay. Of rational function f of x equal to 2x squared over x minus 1 x plus 2. There you go. Alright, so now we just need to find where the value that make the function undefined, which is this one. So which is the denominator, right? In the denominator, we just need to set the denominator different from 0. Okay, or we can set it equal to 0 because this is a vertical asymptote, so that we have to find the equation for that line, right? Alright, so the vertical asymptote have equation x equal 1 and x equal minus 2. So if we do a quick sketch, okay, a quick sketch here. So the vertical asymptote will be here. Let me use it. This is vertical asymptote, x equal 1. So this is the first vertical asymptote. And x equal minus 2. This minus 1, minus 2, right? This is the second vertical asymptote. There you go. So we have two vertical asymptotes. And you just look at the denominator. Okay, and this is the equation for vertical asymptote. Alright, first vertical asymptote, second vertical asymptote. Okay, so vertical asymptote seem to be very easy to find. Alright, and of course, if the function is defined everywhere, for example, in this case, defined everywhere because the domain is negative infinity to positive infinity. So the vertical, we don't have no vertical asymptote. The vertical asymptote over here, I'm sorry, the vertical asymptote over here will be yes, no vertical asymptote, sorry, because it defined everywhere. Okay, no vertical asymptote. It's different from this one, and you know, because over here is 0, over here undefined. Okay, but if it is 0 here, is 0 here, 0 here, 0 squared, so plus 4 is still defined. So there's no point that make the function undefined. It means that we don't have any vertical asymptote. Okay, sin x squared plus 4 is off. always greater than 0. This is true. Okay, so no vertical asymptote. Okay. Pretty easy. I mean, finding vertical asymptote could be very easy. You just look at the denominator. Okay. Yeah. And of course, in order to find, you must be able to factor them out. If it's not factorable, then I mean, you can find it, but it's just hard time. Okay, it's hard time. For example, in this case right here, you have to factor them out. Example number 3. I have k of x equal to x minus 4 over x minus 2 times time 3x squared plus 5x minus 2. Alright, so it looks like in factoring form already, but it's not completed factor. So you have to do one more step. Try to factor this out, okay? If it is factorable, we have to try it. Alright, let's see if it's factorable or not. So we have 3x over here, you have x over here, and you have 2 over here and minus 1. Here you go, you can factor them. So in order to find vertical asymptote, you just set each of them equals 0. Alright, equals 0, equals 0. So you have x equal 2 is one of the vertical asymptote, 1/3, and x equal negative 2. So we have 3 vertical asymptotes. So if we put on the sketch, you're gonna have something like this. Okay. Okay. So x equal negative 2, negative 1, negative 2. Okay, so that's the first vertical asymptote. X equal to 1, 2. That's the second vertical asymptote. And x equal to 1/3. So we have another one right over here. The third vertical asymptote. There you go. This is 1/3. Okay. So we have totally 3 vertical asymptote. Okay. Okay. How about horizontal asymptote? How about horizontal asymptote? So on number 2, horizontal asymptote. Okay. So what is horizontal asymptote? As a horizontal asymptote, it is a horizontal line. It's horizontal line. So, and this is the definition mathematically. When x, okay, if x approaches to positive or negative infinity, then y approach to a value. That's a horizontal asymptote definition. Okay. Just imagine, I have the graph like this. I have a graph like this. Okay, and it's y and x here. And I have a horizontal line like this. And my graph is go like that. There you go. It get really close. Let me redraw this. So my curve is get really close to the dashed line here. Alright. And this dashed line over here is the a value at a. So when x approaches to, you see that when x approaches to positive infinity, okay, and my line, when x approaches, my y is approach to get close to this line. Sorry, this is kind of going this way also. There you go. There you go. So that is the horizontal asymptote. So how do we find horizontal asymptote? We have a rule. Now let's go back to the definition of the rational function. As we know that rational function is a function in fractional form, and the numerator contains a polynomial and denominator contains another polynomial, right? So it means that it must be in this form: a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, plus blah blah blah, plus a0, right? And the bottom here, it must be another polynomial, so it must be b to the n, okay, x to the n, and to the m. Let's do m, x to the m, because n and m is different degree. B to the m minus 1, x to the m minus 1, plus dot 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 b0. Alright. Now I'm gonna categorize this into three cases. The first case is that if n is greater than n, which is the degree on the top is greater than the degree at the bottom, then we don't have fx has no horizontal asymptote. Okay, no horizontal asymptote. If n equal m, then horizontal asymptote will be x equal, will be x, okay, not y anymore, a sub n over b sub m. However, if n is less than, it means the degree on the top is less than the degree at the bottom, okay, then x-axis, okay, which is the equation y equals 0, okay, is horizontal asymptote. Alright, so that is the rule to find horizontal asymptote. Okay. For example, alright, let's say, what if I have something like this? I have f of x equal to ax squared plus 1 over x4 plus 1. So you see that the degree over here, okay, is smaller than here. So the degree over here is 2, is smaller than m equal 4. And if it's smaller, what happened? Then y equals 0, okay, which is the x-axis, is horizontal asymptote. There you go. Because the degree is smaller. Okay. How about this one? Number 2. How about I have ax squared plus 9x minus 5 over 2x squared plus 1. Okay. Alright, so you see the degree on the top and the degree at the bottom, they're the same, right? So the horizontal asymptote, will be what? Will be y equal this over this. A over 2 will be 4, right? Look at that. Go back to the rule right here. Right here. Oh, I need to change a little bit over here. It will be y, not x. Alright, because it's horizontal line. There you go. I change it. It will be y equal to the coefficient on the top over the coefficient at the bottom. See this? Oops. So the coefficient on the top over the coefficient at the bottom. Okay. Alright. Okay, and of course, if it is greater than, we don't have. If it is greater than the bottom, we don't have horizontal asymptote. We already know that. Okay, so that is the rule for horizontal asymptote. And if it is greater than, if the degree on the top is greater than the degree at the bottom, according to the rule, we know that there's no horizontal asymptote. However, they have another type of asymptote, which is a slanted asymptote. Okay, slanted asymptote. So slanted asymptote can be found by doing division. Okay, by doing division. So the quotient of the division, okay, will be the slanted asymptote. Okay, so we know that if the degree on the top is greater than the degree at the bottom, we have slanted asymptote. But not all the time. There's some condition. There's some condition. If the degree, okay, the degree on the top, which is n, is greater than m by 1 degree only, then we have slanted asymptote. Okay, then we have slanted asymptote. If the degree on the top is 3 and the degree bottom is 1, so we don't have it. If the degree on the top is 3 and the degree at the bottom is 2, yes, we do have slanted asymptote. If the degree on the top is 2 and the degree at the bottom is 1, yes, but it's only greater than by 1 degree, then we have slanted asymptote. If it is greater than more than 1 degree, then we don't have slanted asymptote. Okay, but for example, I have something like this. Example number 1. I have f of x equal to 2x squared minus 5x minus 3 over x minus 2. So as long as we know that they have slanted asymptote because the degree on the top is greater than the degree on the bottom, over here 1 will be only 1 degree greater. So how are we going to find slanted asymptote? We're going to use long division, and hopefully you guys do remember how to do long division. Okay, so how are we going to set up long division over here? So we're going to do x minus 2 here, right? And we're going to do like that, right? Hopefully you guys still remember. Okay, then you're going to take this, divide by this, which is give you 2x, right? Then you're going to distribute them back, right? Multiply them back, which is give you 2x squared minus 4x. And you do the subtraction, which is give you negative x, right? And you drop negative 3 down, and this is give you negative 1 and negative x plus 2, which is give you negative 5. Subtract them, give you negative 5 as the remainder. As the remainder. So it means that over here what we have that the slanted asymptote will be the quotient function. Quotient function will be this one. So slanted one will be y equal to 2x minus 1. Okay. So if you see that the slanted asymptote over here is a line, because you see that it is y equal to mx plus b over here. Okay, and it's always like that. It's always has the form y equal to mx plus b because it's slanted asymptote. It's a line. Okay, so remember that. I can do another one here to find slanted asymptote. How about this one right here? Oh, this is a very good problem right here. Example number 2. G of x equal to on the top I have 9x to the third minus 5x plus 4, and the bottom I have 3x squared plus 2x plus 1. Alright, so first you check the degree. The degree is bigger than the bottom, and the degree of the bottom, and it's only bigger than 1 degree. Okay, this is 3 and 2. If this one is 1, then it would be wrong. We don't have slant because it's 3 and 2 and it's greater than only 1 degree. Then we have slanted asymptote. We're gonna go ahead and do the long division. Alright, so we have this. Okay, let's do the long division. We have 9x to the third plus 0x squared, right? Make sure we're missing the x squared. Okay. Alright, this going to this give you 3x. Distribute them back. 3x to the third. 6x squared. Do a quick subtraction. Yeah, which is give you negative 6x squared. Right. Drop negative 5 down. This now 3 going to negative 6 is give negative 2x. Negative 2x. Oh, we give you negative 2 only, not x, because x squared divided by x squared. So negative 2 times negative 6x. Okay, you have to master long division. Okay, negative 2, negative 4x minus 2. Right? Okay. Let's see. I think I missed something. Right? I'm gonna drop this down. I think I missed something. Negative 4x squared minus 2x. I think I missed something over here. Yeah, I think I missed something over here. Okay, let's redo it, because when I distribute 3x times 1, I forgot that. Okay, so this going to that, this going to this, and this going to that. I missed that right here. 3x times 1 is 3x, so over here will be 3x. You gotta master long division. Okay, now we do subtraction. Give you over here will be negative ax. There you go. Okay. Okay. So now you drop. Okay. Then you're gonna drop this down. Okay. Then drop this down. And go to that. Alright. This is gonna get a negative 2. And the time 3 is negative 6x squared. Negative 4x. Negative 2. There you go. You do subtraction, which just give you negative 4x plus 6. And you cannot do anymore because the degree over here is smaller than the degree here. So this is the whole thing over here could be the remainder. And the slanted asymptote here. Slanted asymptote will be y equal 3x minus 2. Alright, so let's put a remark over here so that you remember. Okay, so slanted asymptote it must be in the form y equal to mx plus b. Okay, it must be, because it's a line. Okay, if it is not in this form, it means you got something wrong. And you must master how to do long division. Please go back to the video we had last time, or go back to the lecture we had last time. You have to master long division. Okay, if you have any question with long division, you have to let me know right away. Okay. All right, so that is all the method of finding asymptote. Okay, now let me give you a big problem. So let's see if we can do that or not. Okay. In the example number 3 here, I have function like this. I have f of x equal to x to the third plus x squared minus 4x minus 4 over x squared plus 3x. So the first question I'm asking you to find phi domain. And the second question, phi xy intercept point. C phi O all asymptote. Okay, as you can. Alright. Alright, so let's see how we're gonna do this. Answer. First of all, let's find domain. Okay, in order to find domain, we have to look at the denominator, and the denominator over here is x squared plus 3x. So we have to set x squared plus 3x different from 0, right? Because it's a denominator. Now we have to factor them out. Different from 0, so x different from 0, and x plus 3 different from 0, which is x different from -3 and x different from 0. So there are two values on the number line that we have to exclude. So the domain will be -infinity to -3 union -3 to 0 union 0 to positive infinity. So here goes that's domain. Now we want to find x-intercept point. So you're gonna replace y with 0, right? So we're gonna have 0 over x3 x squared minus 4x minus 4 over x squared plus 3x. Okay, now I multiply both sides by the denominator, so what I have will be this. Alright, so our job right now is to find the x value, which is it's not really that bad. We just go ahead and group them, find GCF over here. Group them, find GCF. Alright, so we have group them and find GCF. Here you go. Alright, so you see that factoring method you have to master. So you have to keep factor them out. So x squared minus 1 is x plus 1 times x minus 1 times x plus 1 again. Alright, equal to 0. Alright, so we're gonna have x plus 1 equals 0 and x minus 1 equals 0. So x equal -1 and x equal to 1. So we have two x-intercept will be 1 0 and -1 0. There you go, two x-intercept point. Now we want to find y-intercept point. So in order to find y-intercept point, you replace x with 0. So you have y 0/3. That's equal square minus 4 times 0 minus 4 over 0 square plus 3 times 0. Alright, so what do you say? You see that over here we have -4 over 0, right? We cannot solve for it. So in this case we don't have y-intercept point. So no y-intercept point. Okay, because you see that it's 0 here undefined, so no y-intercept point. Now we're gonna find all asymptote. Okay, so we already set over here. We set the denominator. Let's find the vertical asymptote first because it's denominator. Okay, so x equal to 0 and x equal to -3 as the vertical asymptote. Alright, vertical asymptote. Do we have horizontal asymptote? Nope. Because the degree is greater. Because sin n equal 3 greater than m equal 2. So no horizontal asymptote. Instead, we will have vertical. We have slanted because it's greater than 1 degree only. So we're gonna do slanted asymptote. Okay, so let's do the division. So x squared plus 3x. Okay, we're gonna do long division. Okay, x3 plus x squared minus 4x minus 4. Alright, x squared going to x will give you x, x3 plus 3x squared. With quick subtraction. Alright, you gotta master long division, okay? Drop it down. Alright, minus 2x. Minus 2x, well, we can give you minus 2. Distributor give you negative 2x squared. Minus 6x. Subtraction. Give you 2x. Drop negative 4 down. And you see the degree over here is smaller. So slanted asymptote will be y equal x minus 2, and since you see that it's in the form y equal to mx plus b. Okay. Alright. So that's all about rational function I want to introduce. And I think I'm gonna stop the lecture over here. If you have any question, please do not hesitate to send me the message through Canvas. And I'll be seeing you next time in the new video. Bye bye.